No. So I started working with the Smalltalk VM earlier than this. I started doing some work with Gilad on Newspeak in 2007 at Cadence, and we added support for read-only objects to the Squeak VM, the standard interpreter VM. And that was the first time that I found out how to use it. But in 2008 I joined Quack, and they wanted, for their 3D environment, a faster VM. And they had this, which was the state of the VM generator at the time. So there's an interpreter where it's context, so every time you send a message, that activates a method, you allocate a new context, and you have to copy arguments from one to the other. And then when you return, you have to return back. And that's the standard VM definition that you see at the end of the smalltalk-80 language in its implementation book. And it's defines effectively the ABI that the VM has to maintain, because lots of things are built on top of context. It's the debugger, the ability to serialize processes, the scheduling model, etc. But it's slow. So the first thing to do was to produce a fast JIT. But Quack were in the business of getting this system, keeping the system working. So they asked me to deliver the various components in as many fine-grained increments as possible, so that there wouldn't be the risk of me not completing. It would minimize the risk of me not completing, and that they would get value sooner. So when you do a JIT, you want to map those contexts to stack frames. So instead of actually allocating context on every message sent, you have a much more conventional organization in the machine that looks like that you'd have in a C program of just stack frames. And contexts, you do create them, but they effectively serve as proxies for stack frames. And you can't see this from Smalltalk. It looks like everything is still made of context, but under the hood you have these stack frames. So that's a complicated piece of code that manages this mapping. And so the first task was to implement that. And to implement that, I also needed to change the generator that converts the Smalltalk code to the C code that's actually compiled to produce the VM, so that instead of just having the ability to translate code that was in a single hierarchy like we had here, that we actually can start to deal with more than one hierarchy. So the stack interpreter was its own class, and then there was object memory. Object memory had some problems. The object representation in this, which is the V3, the pre-spur thing, is kind of complicated. There's 3 sizes of objects depending on how many words of header. So you can have a 1-word header with a little field in it which codes up to 32 classes, or you can have a 2-word header which has a full word for class, and then a 3-word header where there's room for a much bigger size. So large objects are 3-word headers and stuff. And that means that, allocating an object is quite complicated stuff. But there are other things like the hash inside the object was actually constructed with a pseudo-random number generator. And it was run when you allocated the object. So every time you allocated an object, whether or not you accessed the hash, you would have a read, modify, write cycle for this pseudo-random number generator as you read it and folded it over to the next step and wrote it back. And so new object memory had a few little tweaks, like deriving the hash from the new space pointer by taking a hash of that and getting rid of that read, modify, write cycle. And then the translator needed more sophistication, this idea of being able to have struct types for very simple object types. And so in the stack VM, there's an object which holds onto stack pages on the right. And then stack pages holds onto a collection of stack page objects. Sorry about that. So that is the stack VM. So if you can't compile a JIT right now you can take this VM and you can produce, for example, a VM for the iPhone, which just has the stack thing. And this thing goes about 50% faster than the interpreter, depending on how send-rich the benchmark is. I mean, this optimizes sends and nothing else. Primitives run the same speed. Garbage collector is a little bit faster. So then the next thing to do was to add the JIT. And the orange stuff here is the JIT. And it's called the co-JIT because, it's a pun, but it sits alongside the co-interpreter. So the co-interpreter knows that it has machine code associated with its methods, and then it can run that machine code. And the JIT knows that it's producing machine code for the interpreter. And the trick in the VM is that the first word of a method in our family of smalltalks is an integer that encodes things like how many literals I have and what primitive I have and how many arguments, etc. And that is replaced in the VM with a pointer to the machine code. And if everywhere where the VM accesses a header, it hides that fact and it works out, oh, this is a method that has machine code because that pointer is now just a pointer and not a small integer. And so it's able to associate the machine code for a method with the method by having that pointer and hide it from you, and you don't see that happening. Now, I knew that I was unhappy enough with the object representation, that it was so clumsy, that, for example, the only object allocation that the JIT is able to do is to create floating point number results, which are actual proper objects, as the result of the floating point primitives, but none of the basic new primitive or the basic new colon primitive or the creation of this context or anything like that is done in machine code in this, so it's kind of slow. But I knew that I wanted to go better than that. So when I implemented the JIT, I introduced this abstraction of an object representation that would sit between the JIT and the decision of how to access object fields and how objects were laid out in memory, so that I could then change the thing going on in the future. And in 2010, Quack allowed me to release the VM as open source, and we finally had the COG and the stack VM, and at that time we only had an x86 backend, and we generated sources version via Subversion. So you develop with this Smalltalk program, and when you want to produce the real VM, you have this thing called slang. Slang is either the subset of Smalltalk in which this is written, or, as I think of it, it's the compiler that rewrites the Smalltalk to the C. And so, Bert has one definition, and I keep on getting it wrong, is that slang is the language, but for me, slang is this horrible compiler that I struggle with to get the C produced. And because I have to keep on making it more complicated. What you do is you generate C from the Smalltalk, and then you compile that to produce your VM. And I made the decision that I didn't want that process to be part of the build process. I wanted there to be an intermediate step, which was that when you created the sources, you held on to them and you versioned them, because if you're debugging your VM in production, you need to find that. You don't want to go back to the Monticello package and regenerate sources. There could be any number of reasons why you didn't generate exactly the same code. Right? So you really do want to version it. So at that time, we piggybacked off the standard repository for the platform support libraries in the VM, which was Subversion, and it doesn't support collaboration well, doesn't support branching well, and people in the community felt very restricted because basically it was a very small number of developers who had write permission to that Subversion repository. Okay, the next step is that in writing the JIT, again there was risk. I had become familiar with Peter Deutsch's JIT for VisualWorks, and that speeds up sends not just by doing this context to stack mapping and having inline send caching, but it also maps the receiver and the last two arguments in any send to registers. So that means when you invoke, for example, the output primitive, the receiver, the index, and the object that you're storing are actually in registers instead of taking them from the stack. So it has a nice, fast calling convention, and it also does some clever things with the bytecodes that code for greater than or less than. That it looks at the greater than, and if it's followed by a branch, it generates code which says, okay, if these two things are small integers, let's just use the machine version of comparison and jump on the condition codes. Whereas what you do notionally in Smalltalk is you run the comparison primitive, and that produces either the true object or the false object, and then the bytecode has to test on the true object or the false object. And that's a lot more work than just doing the comparison and jumping on the condition codes. So the first version of the JIT didn't do any of that clever stuff, but I knew I wanted to. So that's like cog v1, and then cog v2 is we added the stack to register. I added the stack to register mapping cogit, and that was a time when life was bad at Quack, and we'd had a new management team coming in, and they were trying to get us to produce a new release, and I had a visit planned with Marcus Denker, and I was going to work on this, and I decided to work on it, and they fired me and had to take me back as a consultant, which was fun. And this allowed the VM to go a fair bit faster. So let me skip forward a couple of slides. And this is basically the performance. So the interpreter down there, the stack was a little bit faster, and then cog v1. I don't think these numbers are right, but it more or less the sizes are about right. And then cog v2 is this more sophisticated JIT that gave us maybe an additional 20-25%. But then there's some other work going on. At Cadence, we were using cog at the bottom of Squeak with Newspeak to build the solution at Cadence for phone design, and we decided that we didn't want to live with the constriction of the Squeak bytecode set. And I'd done some work with Klaus Gittinger, and we'd added support to the multiple for multiple bytecode sets, support to have the JIT and the interpreter support two bytecode sets at the same time. And so we designed the Newspeak v3 bytecode set. And the big change in the Newspeak v3 bytecode set is that it uses an idea from self, where instead of having like a short form bytecode for push instance variable 0 through push instance variable 15, and then a long form bytecode, you keep that, but the long form bytecode can be extended by having prefixes. And so you introduce two bytecodes, prefix A and prefix B, and they kind of accumulate. So if you have two prefix A's, you can build up a 65,000 constant. And if you have two prefix B's, you can go from minus 32,000 to plus 32,000. And the long form bytecodes check for the presence of these extensions. So the extensions accumulate in two variables, and then the long form will take notice of them, which means that the short form bytecodes still run quickly because they don't have to check for these extensions, and they have very high dynamic frequency. And it's the long forms that have the low dynamic frequency. And so it's not much of a cost, but it lifts a lot of limits. So that's the basic thing in here that was new. So then now I've moved to Cadence, and Cadence wanted these rather large phone models to be able to continue to scale, so it was very important to have 64-bit support. And my work at Park Place, at what was then Syncom, when I did the 64-bit VM there, was to change the object header so that instead of the object header including a class reference, which would mean 64 bits in a 64-bit image, which is a very, very big overhead, right? Imagine 64 bits of header giving you size and hash and all of that kind of information, and then there's another 64 bits for the class. It's a really big overhead. So instead you have a 22-bit field in there, which is a reference to the class, and it's an index into the class. So if you want to find the class, you have to go and take that index and index a sparse table of classes. But that key is all the VM needs for looking up classes in hashes, in the inline caches. And so that means that you now have a single 64-bit header, and it's common to a 64-bit and a 32-bit representation. So it's much easier to write the 64-bit support. So anyway, Spur, because of this simple single header, was able to do much more allocation work in the JIT. So now there's a new primitive. When any object that's big enough to fit in new space will be allocated by machine code. It's much, much faster to allocate. Whenever you created this context object or a block closure object, that's created with machine code, not very slow, going into the interpreter's runtime and C code to ask it. And so Spur goes a lot faster because the garbage collector is quicker, because the object representation is simple enough for the JIT to generate code to allocate objects. And at the same time, Tim Rolich provided another back-end to the JIT, and we worked on that together. And so we had ARM v6 support, and my abstraction of the object representation to allow you to subclass for the JIT, to insulate the JIT and generate code for either the v3 or the Spur object representation works. And the way to think about that is that when you punch out the VM, you choose which code generator to include, and you choose which object representation to include. So you'll push out a different set of sources for v3 and x86 to v3 and ARM, and a different set for v6, for Spur and x86, etc. So there's a lot of different files on disk when you generate them, and when you come to build the VM. Spur was released as Squeak 5 and Faro 5, and it's been in use for about a year. And then this year we released the 64-bit version, and so now we add a 64-bit memory manager here, and the 64-bit object representation, and lots of changes to the internals of the JIT to make sure the code was 64-bit and 32-bit clean, and all of that kind of stuff. And that is released as Squeak 5.1 in 64 bits, and Squeak Faro 6 is in preparation. If you want to think about the performance, then Spur gives us about 40% better performance than the V2, or is it? Yeah, it's about 40%. That's right. And a lovely thing happened. The community persuaded me and others that moving to GitHub would be a good idea, and for me it was. It's been a very positive change, but the nice thing is that I haven't had to move the Smalltalk. That still lives in Monticello. It's only moving the generated sources from their Subversion slum into the lovely GitHub thing, and it's been a really positive experience. Lots of people have come and helped do that move and produce some really nice stuff, but many more people have come and started working with either the platform sources or with plugins, and we also have new people working with the core VM. So okay, that's kind of the state of play now, and an idea that I've had for a long time, since 2002, is to add an adaptive optimizer to Smalltalk, but to write the adaptive optimizer in Smalltalk and have it live in the image, and not have the adaptive optimizer in the VM as a traditional one. And in 2012, I was really lucky to be approached by Clément Berra, who's a PhD student in Eliot, and we've been working on this for a long time. And Clément is ready to release. And so the idea here is in the bytecode set, what you want to do is do bytecode to bytecode adaptive optimization. Well, if you do bytecode to bytecode adaptive optimization, you can inline several methods, several bytecode methods in a single bytecode method and eliminate things like closures. You know, you could inline the loop over a dictionary so that you didn't create any of the closure object that you were applying in the do, right? And so that's great. But how are you going to do the kind of things that other adaptive optimizers do, like realize that, okay, when we do the at on the dictionary, because the variable is from 0 to the dictionary size, we don't need a bounds check in the at primitive, right? So how do we do that? And if we're doing bytecode to bytecode optimization, it seems that you have no way of expressing that. Well, back in the day, in the Parkplace VM, Peter Deutsch had been doing some experiments, and he'd added something to the bytecode set, which is a set of primitives, which were unsafe. And he was trying to figure out why the speed of Smalltalk, how fast of the speed of Smalltalk could be compared to C. And these were things that he just put in as experiments. He didn't have a way of knowing when it was safe to use those primitives. But with inline caching and a whole set of ideas behind the self VM, we now know that if we look at the caches, they will give us useful type information, predictive type information that we can use. So what you do is add to the bytecode set one bytecode which says, okay, I code for one of 256, or is it, I think it's 65,536 primitives, of which we've used about 60 so far. And these primitives do things like say, okay, I'm going to access an object, and I'm going to assume that the argument is an index and it's in bounds. And so for that, you just generate 2 instructions to index the object instead of the whole humongous at primitive. And so there are those kind of bytecodes for comparisons and arithmetic and allocating objects and accessing objects, etc. And because they're unsafe, it's only safe for an optimizer which has done a type analysis on the code to generate them. But because they're unsafe and they're very simple, the JIT can generate very small amounts of code. So that's one part of it. That's why the bytecode set is really important. And Sister also uses the prefix idea, so we've lifted a lot of limits, and you can have 32k literals in SPUR as opposed to 256 literals per method. You have bigger jumps, etc., because of the prefixes. And because the optimizer wants to know that literals won't change, and that it can guarantee what their class is when it makes the optimization, we also added the read-only object support that has a bit per object that will prevent you from modifying the object and causing the output primitive to fail, or if you try and modify the instance variable of an object with this bit set, you'll get a message, a bit like does not understand, you cannot assign to this object happening. And that's the kind of support that Gemstone uses. And so we can use that for both the optimizer and a putative Gemstone interface. Okay, so in the VM, as far as the JIT goes, there's a register allocating cojit, and we haven't quite got this working yet. So register allocating cojit it's going to work very soon, but we've definitely got the sister cojit. The register allocated cojit is something that when we're doing our analysis of the bytecodes, it allows us to map temporary variables into registers and have much better code there. And then what the sister cojit does is add the stuff that you need for doing the adaptive optimization, which is basically the bytecode for if true. If you think that the way that if true is compiled, if true gets compiled into this bytecode, which is pop and jump on true or pop and jump on false. And what we do is associated with each bytecode, pop and jump on false and pop and jump on true, 32 bits, which is 2 16-bit counters. And one is, I've reached this instruction, so I've executed that instruction, and the other is, I've taken the branch. And so if the reach thing goes to 0, the effect is to send into the image and say, hey, a counter's tripped, at which point the optimizer kicks in. And the optimizer is able to look at the stack as contexts, because that abstraction is maintained, that illusion is maintained, and you can have a look at however methods they are, and there's a primitive to say, okay, for this method, what's the state of your inline caches? And so it takes all of that information and it maps bytecoded methods into static single assignment and decorates it with this reached information and type information, and it does some analysis and inlining, and then it does SSA to bytecode, but it's bytecode plus the go faster inline primitives, and then that is installed in method dictionaries, and then the next time you run this optimized method, the JIT generates the much better code. And so the beauty is we have an adaptive optimizer that's quite complicated, but it can be implemented purely in Smalltalk. It's much more elegant than in slang, which has kind of got C-level control structures, and we have the ability to save an image hot, so the system doesn't come up in a cold state. We've got optimized methods there, and we can actually develop new optimizations. And so we hope that this will be a very fun context for PhD students who want to do work on adaptive optimization, because the tools are great, etc. And Clement is going to be writing up early next year, and the first release of this will be released around about Christmas. And so now, in System V1, our first release, we expect to have something around a factor of 2 faster. This is for a specific binary tree benchmark, and the binary tree benchmark is dominated by GC performance. So we don't see the factor of 2 performance that we see in others, but we expect that the performance we're able to extract with Sister will climb, and looking at other adaptive optimizing VMs, we would expect to get a 3-fold to a 4-fold increase in performance on our base for certain computational benchmarks. So that's where we're going. Sister is like a factor of 2, but we hope to get a factor of 4. And there's a lot of people, a lot more involved now, and so Tim has been involved in the JIT. Clement is responsible for the adaptive optimizer, and he and I work a lot on the JIT. Nicolas Cellier has done floating point math and a lot of work with optimizing large integer arithmetic. Fabio and Tim at Potsdam have helped, have been the main engines behind the switch to GitHub, and do work on graphics, and there's other people do work on the SSL plugin, etc. Ryan Macnack is at Google. He's been working, doing all of the Newspeak bytecode work and modifying the JIT to have the Newspeak lookup semantics. John McIntosh has been involved with the map integration and the GUI, and Craig Latter has done work with his snow globe, and there's many other people coming in and getting involved. So that's kind of where we are, and you know we'll keep on going. But right now, on the very short term, we'd like 64-bit ARM, which means an ARM v8. We'd like to fix the broken compactor that I wrote very quickly for. It was actually the second compactor that I wrote for Spur, which is broken, and we'd like to add an incremental GC so that there's no pauses when you do a global GC, that you can rely on the thing, and it can support it can support animation. Okay, well that's it, and I think I finished in exactly 30 minutes.
First of all, it's nice for the people who are interested in VM and we don't know much about it to have a contest. But I think that most experts and people working with the VM have been doing so for about, I don't know, more than 10 years, and there's quite a high entry barrier. For example, all I've heard now was really interesting, was really technical for me, and I would like to ease the development of VM, but as a beginner, I don't know where to start. So, what would you recommend that we get information or documentation of the current VM, besides evolved and everything? Thank you.
So there's 2 parts to that answer. One is that Clement, as part of his teaching, met exactly this problem. How do I provide this very big mountain of complexity in a usable way? he's written a book where he introduces a smalltalk subset that introduces a basic interpreter and then the stack and then a JIT. So that, one thing is to use his book, but the other is we're really friendly, and you can, there's Laura has joined us. Laura Serrato has joined us and started doing stuff with plugins, and you found that we were communicative. So you just have to be prepared to say, okay, let's get together on Skype and give me a look, right? Give me a tour, right? And so you can ask Clement to give you a tour. I'm happy to give you a tour. Nicola will, and we just have to find a time, and we'll do it. But the real way to make it easier for people in general is this kind of book approach, I think. And really it should be an online book, something that we can edit and tweak. But let's talk and set up a date, and I'll, quick.
There's also quite some number of European and Argentina working players, so maybe we can talk.
Okay, thank you very much.